Welcome back to this session. So today we have invited Professor Dr. Murthy sir, who is a well-known, renowned scientist and doing research in machine learning and quantum computing. Sir has received his PhD degree in computer science from Purdue University, USA. In 1989, he worked as a member of technical staff at Belcore, United States of America. After returning to India, he worked as an associate professor at IIIT Hyderabad before joining Mahindra University. Sir is now working as a professor in Mahindra University, Hyderabad. He has about 20 years of teaching experience. He has published many reputed journal papers and presented papers in conferences and workshops. And Sir's research areas are in machine learning, communication systems, performance evaluation of computing devices, and design of autonomous driving vehicles, Internet of Things, etc. He is a senior member of ACM since last 10 years and a senior member of IEEE as well. He received many awards, including Rashtriya Gaurav Award. Now, sir, session is yours. Thank you for accepting this invitation. I am thankful to you, sir.
So, thank you, Professor Jamal. I hope I pronounced your name correctly.
Jamil.
Jamil, okay. I had a friend by name Jamal long time ago. Yes. You see, like, even though the topic was given as foundations of deep learning and computer vision, what I felt is people come from varied backgrounds, and sometimes my friends like Professor Hassan and Professor Priya from math department, physics department respectively, what I decided was to give the foundations of artificial neural networks, because convolutional neural networks originated out of the limitations of artificial neural networks. Okay, so without further delay, here are the goals of the talks. Generally, when you attend an FDP of this nature, there are varied types of audience. Let me put myself in the shoes of faculty members. When I put myself in the shoes of faculty members, sometimes you are asked to teach a course, and that course was part of your bachelor's or master's or PhD coursework. And then what happens? You are familiar with the kind of concepts, and then what you do, you kind of deliver the lectures and you are fairly confident. But sometimes what happens, you are asked to teach a course and you never had any background in that area. So what do? You collect a book and read. And when you read, you digest maybe 80% of it. And then what happens? You go and sometimes a question comes out, and the question is kind of a very new one to you, and you somehow manage the show. So why I said that is, first of all, I would not like to assume any background on your part. I would not like to assume that you already know artificial neural networks. And bear with me if you already knew artificial neural networks. So the first part of the lectures will be on artificial neural networks. And then we go into convolutional neural networks, which you are kind of familiar. And when we use the word foundations, basically there are two paradigms in deep learning. One is deep belief networks by Geoffrey Hinton, and the other one by Fukushima, convolutional neural networks by Fukushima and who else? LeCun and others. There are a lot of names there. So, first, the goals of these talks are to give clear explanation of the collection of concepts associated with artificial neural networks, ANNs, basically. The second part is to trace the development. See, I'll be honest with you. Sometimes there is a book by Satish Kumar which is out of print now on neural networks. It is about 700 to 800 pages. And Professor Zadeh, Lotfi Zadeh, he came out with fuzzy logic, and Professor Zadeh coined the word soft computing. How many of you heard of soft computing? Raise your hands. So, fuzzy logic, artificial neural networks, genetic algorithms used to be typically part of soft computing. Nowadays, IEEE has a separate journal on evolutionary computation, particle swarm optimization, ant colony optimization. There a whole bunch of them came out. Whole bunch of things came out. Why I said that is, in books, sometimes the author knows how a concept came into existence. Sometimes he just writes down the equation and then proceeds. Main question for participants like you is, how do you write such an equation yourself? See, you understand the equation, but how did the equation come about? What is the thought process? What is the logical reasoning behind writing that equation? And believe me, I tell my students, when you see equations, don't get nervous and don't become defensive. The confidence of attending my lectures is to develop an ability to write the equation yourself, which is not taught in any book. Okay. So we will trace the development of the research area of artificial neural networks. Generally, a research area is currently starting in Western countries, or Europe, or Japan, or United States, UK maybe. And what we are doing, we are playing catch up. Now, that need not be the case. So we will go into technical details. That something is motivational. That need not be the case. That is from Manu. You come up with a research area which other people pursue. See, for instance, from Hyderabad, there is something called DNA fingerprinting. Okay? CCMB, there was a director, I forget his name, director of CCMB, he was the first person to talk about DNA fingerprinting, and now it's popular all over the world. At IIIT Hyderabad, there was a faculty member, he asked a question. Generally remember, what is science fiction today may be or will be a reality in 10 years. Today it is science fiction, but in 10 years it will be a reality. So here is the main point that I would like to tell you is, when you watch cricket, right? When you watch cricket between Pakistan and India, or Australia and India, you watch the World Cup. And now, in my generation, when we were listening to cricket, we didn't have televisions. It was only radios was there. So one professor said, can we replace a manual commentator by a machine? It's a very typical computer vision problem. What is the computer vision problem? You have mounted a bunch of cameras. See, the third umpires, sometimes they play back and then decide whether out or not out. So, the cameras these days, they are very powerful. So they are watching the whole game, like your CCTVs. Now, from the input that you get from the video that you get from a camera, can we give a machine to give running commentary? And that professor, and there's a group of them at IIIT, still doing it, I believe. And it was a New York Times news, and one professor became fellow of pattern recognition. I don't know how much he really did it, but he became a fellow of pattern recognition group, International Pattern Recognition Fellow. So the area is called computational sports. The area is called computational sports, and I had my master's student who was working on soccer. He wanted a running commentary for soccer. He developed, using convolutional neural networks, he developed a system which gives commentary. And Star Sports gave him about 15 lakhs for a project. Now, why I said all of that is, from one, you have to develop the self-confidence. See, initially everything looks like science fiction. But science fiction becomes a reality in some number of years. So, we will trace that. See, generally a research area, people take baby steps. Like in math and physics, you take small baby steps and gradually build it up. Now, what are the current trends? What are the current research directions and research problems? So, I kind of, along the way, I will try to tell some current trends, research directions and research problems. All through this is, I'll be honest with you. We can have a lot of discussion. Gauss once made this statement, and I'll come back to it. He said, mathematics is the queen of sciences, and number theory is queen of mathematics. He made that statement. But see, engineering is equally challenging. Hilbert once said, paper and pen exercises are very easy. To build a fan, to build a light, you need equal talent. So, don't have an opinion that engineering is easy. Engineering has its own challenges. Pure sciences have their own challenges. Okay, now, some applications, and then I give you some good references and books. Why I put the fifth one is, particularly some of you who are trying to learn a new area. Like for instance, in deep learning there is an area called adversarial machine learning. Adversarial machine learning. That is, when an adversary wants to fool a deep learning system, how does he do it? See, it's kind of very scary. We are going into machine learning, but when we really go into machine learning, the problem is, sometimes just like every technology brings with it some problems. It brings with it some problem. Like you had email, you had the computer networks. But what happened? We got viruses, we got ransomware. I encrypt all the files on your machine. Then only if you pay me money, I'll decrypt it. Otherwise, I won't decrypt it. So, why I said that is, machine learning and artificial intelligence are currently popular areas, but somewhere down the road, we run into problems with automating everything. When you try to automate everything using artificial intelligence, we will definitely run into problems. Okay? So now let's get started. Okay. Alright. So first part of my talk will be spending some work on physics, because for those of of you from pure sciences or even computer science students or information technology students or any electrical, mechanical, chemical and civil engineering students, you run into what are called as differential equations. And all of you know what a differential equation is. But currently, to solve differential equations, if you are lucky, you get a closed form solution to a differential equation. But closed form solution is most of the cases not possible. So what you do, you discretize the differential equation. You discretize the differential equation and use numerical procedures to solve differential equation. Two scientists, two researchers, pure mathematicians, they wanted to see if differential equations could be solved by artificial neural networks. See, pure mathematicians, what they did was, they proved a very nice theorem called function approximation theorem. So, ideally I wanted a blackboard, but that's okay. Suppose you have a kind of closed form solution, then you are done. So what these people did was, can we use that's okay. Yeah. Just let's get back. Let's get back to the presentation.
Play button.
Okay, thank you. So here it is. We have some inputs. We have a black box representing the artificial neural network. We have some outputs. Now the question is, we train it. We train the neural network. Here is, so basically, suppose the inputs are represented by x1, x2, xn. And the outputs are represented by y1, y2, yn. y1 is some function of x1, x2, xn. y2 is some function of x1, x2, xn. And so on. Now, what mathematicians did was, the so-called backpropagation algorithm can exactly approximate any function. So that's called universal approximation theorem. So, solving differential equations is kind of bread and butter for astrophysics people or any science and engineering disciplines. Solving differential equation is a bread and butter. So one of the foundations of deep learning is to prove something like the function approximation theorem, universal function approximation theorem. The problem is like this. For multi-layer perceptron, the proof is done. But what people are trying, and see, for Professor Hassan or Dr. Priya, there is no clear-cut mathematical explanation of why convolutional neural networks are working. It's like magic. They are working, they are giving better than human accuracy, but nobody knows. It is not like totally dark. Some baby steps, some baby ideas are there, but currently there is no clear-cut explanation. of why convolutional neural networks work.
That's what they call their black box.
Yeah, that's why they call it black box. Alright. So, Homo sapien living. So, I will spend this slide on spending some time on summarizing physics as much as possible. So, we have the Homo sapien living machine or animal. If you don't believe in God or you believe in God, that's a religious discussion. Let's not get into it. So, when you take the non-living world, first efforts to kind of look at the scientific method is by Aristotle. So, Aristotle thought that force is directly proportional or velocity F equals mv kind of a statement he made, but it's false. Any rate, then as time progressed, Galileo gave his laws of motion. I'll be summarizing physics because there are what are called as pins. Physics informed neural networks. Physics informed neural networks. Rough idea is like this. You approximate a derivative numerically, and when you have the loss function of the neural network, that loss function is captured by the differential equation. If there is any deviation through the back propagation process, the differential equation is approximated, so that you get a solution after several iterations. That's the rough idea. So it's in our interest to kind of spend time on basic physics. So coming to the point, Galileo written down a book on laws of motion. He was observing the pendulums moving inside the churches, and he was trying to give a scientific explanation of the motion of pendulum, and I'll come back to it in a little while. Then what happened, people have tried looking at nature from a purely scientific viewpoint, and there is something called as Galilean principle of relativity. That is, the laws of physics. Simple explanation. You are at a train station and the train is moving with constant velocity, and you are on the platform. The laws of physics in the platform reference frame and the laws of physics in the moving reference frame at constant velocity, right? And so it turns out Galilean principle of relativity is laws of physics are invariant under linear transformations. Okay? It's a simple exercise you do in high school maybe. That is, how these reference frames come into existence is, you are given a coordinate system, XY, rectangular coordinate system. And what did I do? I moved the origin to a different point. Now, I have the original reference frame and I have the new reference frame. Can you give the equation for the coordinates in the translated reference frame given the coordinates in the other reference frame? And you can, it's a small exercise. The other one is, take a reference frame, namely the coordinate axis, rotate them with some angle. Now, if I have the coordinates x, y in the original reference frame, and I have the coordinates x prime, y prime, express x prime in terms of x and y and theta. Theta is the angle through which you shift it. This is the basic explanation. So Galileo did the hard work and he gave the Galilean principle of relativity. comes out here, he suspected that something is wrong with gravity. He suspected, so what he did, he went to the Leaning Tower of Pisa and he took two different weights, dropped them. Two objects with different weights and dropped them. And to his surprise, both of them hit the ground at the same time. So, Galileo didn't have an explanation. A lot of it was dormant for a number of centuries. I'll come to that. So the next major development was by Newton. So what Newton wanted to do was, he was aware of the Galilean principles of motion, laws of motion, and then what he did, he wrote down the three laws of motion. The second one being F equals ma. But just before Newton, Kepler had a lot of astronomical data available, collected by Tycho Brahe and others. Right? Now, what happened? When all this vast amount of data is available, we wanted to understand the laws of planetary motion. So the first Kepler's law, and your GPS works on what Kepler did. Kepler had an idea what's called triangulation. So if you can specify the position with regard to three reference frames, you can uniquely locate it on the planet or anywhere in the universe. And GPS, you need 4 satellites instead of 3 because there is something called clock skew. So first Kepler's law was the planetary motion is elliptical. It's an elliptical orbit. And Newton must have the ability to come up with the differential equation governing F equals ma. That is, what he said, the orbit observed is elliptical, and we know that F equals ma. M d square x of t over dt square. It so turns out that if this force is inversely proportional to the square of distance, then the solution to the differential equation becomes an ellipse. And all this work, he came up with gravitation. Fortunately or unfortunately, Newton thought gravitation is a force, and he coined the concept of instantaneous action at a distance. Instantaneous action at a distance. Why I am quickly summarizing is, we will get to the technical part. So the first part is that 3 laws of motion, with classical mechanics becoming so successful, people were looking at everything from a scientific point of view, heat, electricity, magnetism, and so on. Then Maxwell, James Clerk Maxwell, had the vector algebra available by, let's say, Hamilton and others. So what did he do? He took the vector algebra, and Michael Faraday had these laws of electromagnetic induction. He took the experiments, he converted them into equations. It is not so straightforward. There is something Maxwell did which was kind of remarkable. So Maxwell came out with the theory of electromagnetic field, and Maxwell's theory predicted that light is an electromagnetic wave. So the theory was extremely successful in producing electromagnetic waves and using them for communication. So now, here is the main point. The main point is, Michelson and Morley, they did an experiment. They wanted to know whether light travels at a constant velocity. Whether light travels at a constant velocity throughout the universe. So, Michelson-Morley experiment almost exactly calculated the velocity of light. Okay? Now, here's the issue. Lorentz knew that velocity of light is finite. It's not infinite. So, Lorentz took Galileo's idea and asked a question. What if the reference frame moves at the velocity of light? Galileo never worried about the velocities being comparable to that of light. So when the velocities approach that of the light, length contracts and time dilates. So Lorentz transformation was already there. See, generally you got to remember, science, sometimes genuinely, different people come up with new ideas at the same time, more or less. So Einstein was not familiar with Lorentz transformation. Einstein was not familiar with Lorentz transformation at all. So he asked, suppose I am here in this corner. Let's say I am looking at a stationary object or a moving object. Now, the object is at some position. Now, for that to be perceived at the origin, there is some delay involved. That is, space and time, they are not independent variables, but time is the fourth dimension. So, special relativity was mainly dealing with linear transformations like Lorentz transformation. The next question mainly comes down to is, how can we say, how does the nature know the reference frame? How does the nature know the reference frame of you? To change the laws of motion or to change the laws of physics. So he suspected, he went back to the Galileo's experiment, and there it is that the gravitation is not a force, but gravitation is due to curvature of space-time. Gravitation is due to curvature of space-time. That explains the Galilean experiment. And general theory of relativity came out. All this summary about physics was to tell you, the summary of physics was to tell you that physics informed neural network, very hot area. Lots of people are working in that area. So physics informed neural networks is a very, very interesting research direction. So the Homo sapiens had the acquired needs due to the habit of concentration, art, mathematics and science and technology. Of course, there are higher pursuits like discovery and invention. And most of you possibly know that a discovery is something which is already there, but you are the first person to perceive it. You are the first person to perceive the discovery. Whereas